Hello, my name is Travis Coe. I am a junior computer engineering student at the University of Houston, and this is my final project for ECE 3441 Digital Logic Design under Dr. Marpaung using Altera DE0 Nano. The project I am doing today is the final lab for the class, which is the musical calculator, and it works kinda like this. Essentially, every button you hit adds to the binary count on the LEDs on the DE Nano, and it will play a pitch according to that. So one, if you want to add one, because this only adds, obviously, if you want to add one, you hit the first button. If you want to add two, you hit the second button. If you want to add three, you hit the third button, and each of them are in a rising pitch order, and there's 8 buttons, so there is a complete octave going from C to C. As you look at the LEDs, you can see that they add up as if it was just a binary counter, so that, like, if I hit like the add 2 button and then I hit the add 2 button again, instead of the number 4 coming up in some form of base 10, it will come up in binary, and thus the third light will show up. Okay, so for the physical assembly of the circuit, you got to start with the speaker, and you can just place it anywhere. This is a 2-pin speaker that was provided to us by the professor, and it works both ways, so you can have it inputting on one or the other. It doesn't matter how you can't have it backwards, essentially. And also, we got 8 of these 4-pin push buttons. I pushed it a whole bunch there, but I muted the audio because there's a whole bunch of annoying sounds going over there, and you just basically need to place them down. I spaced them with 1 extra bit apart, and here I'm spinning it up because it took forever to finally lay all these buttons down. And on each of these buttons, there's going to, the bottom part is going to be it's going to be connected to ground. And so here's me trying to show off the wire. The camera constantly got out of focus because of the way this webcam works, and so that was really frustrating. And you'll see my hand move in front several times here. But basically, I'm connecting all the bottom pins to ground. And the other side doesn't matter because basically they both work as 2 independent sides, even though they would both switch on the button press. And all the stuff going on in the background will be in the back half of the breadboard is explained later. But you also need to connect we used a 100 ohm resistor from the positive rail, whereas one end is connected to ground, the other is connected to the VCC, which I believe is a default 5 volts. Could be wrong. I'm trying to show the resistor in focus so you can see that it's 100 ohm. And basically, I connect the other pin, which is basically 2 spots up from the ground on each of them. So basically, I connect each of the upper pins through a 100 ohm resistor through ground, because that's the proper way to assemble this correctly. And from this point, there is a technical split in how you want to build this, because from right here, you can theoretically almost be done with this entire assembly. However, here I am refocusing it. However, there is a protective speaker driver circuit that you can also build. Here is the speaker driver circuit for this musical calculator. Not all parts have to be the exact values specified. I don't even have the right value resistors for most of this. One of these parts also doesn't function at the moment, so I had to make it work without the speaker driver circuit because it totally functions without it, but you run the risk of blowing out your speaker. And here is a photo of the actual, speaker driver circuit built. The green wires are the points that would go around the speaker. And here is the portion where I'm putting the little cable connectors from the pins into the breadboard. And the first thing you want to do is the output pin that sends the ones and zeros in a alternating pattern into the speaker. And that one, if you have no speaker protective circuit, you can put that pin directly into one end and connect the other end to ground. Again, this isn't recommended, but it still functions as exactly as intended. And then here's where I'm showing the ground and the VCC cable, and I'm hooking those into the positive and negative rail as expected. Nothing crazy there. And then from here on, I am connecting in the individual button input pins into where the 100 ohm resistor is plugged into, so the top portion of the button. Here's some testing. As you can see, that third button isn't plugged in, so it takes a little moment for me to push it back in and make it work. And this is just demonstrating how, again, without the protective speaker driver, it still functions, but I wouldn't hold down the button for an extended length of time. And so here I'm just going to show the LED shining again in a certain manner, and that's about it. Okay, the code portion of this lab. I'm not actually allowed to show you the code by the rules of this assignment, so I am allowed to talk you through and explain how the code interacts with the DE Nano stuff. So obviously at the beginning of the code, you're declaring a whole bunch of values and your inputs and your outputs for the LEDs and the individual pin for the signal sent to the speaker, a clock input obviously because this is going live time. I have a whole bunch of registers for counters, and I start everything off at some default initial value. So at the beginning at every time the positive edge of the clock hits, which for this DE Nano thing is 50 million times a second, aka 50 megahertz, a counter will increment by 1, and if that counter hasn't hit a certain amount yet, the signal to the speaker will still be 0. If it's hit a certain amount, it will hit 1, and once it's hit a certain amount even further, it will shut off, and that's set to exactly the same length that originally triggered it into turning on to 1. So essentially it essentially loops between 0 and 1 at a set interval given to the loop, and this is going constantly every single edge of the clock, every single positive edge of the clock. And this is how you're creating a frequency, because it will turn 0 for a certain length of time, 1 for a certain length of time, and since it goes 50 million times, if I set it to that marker point at say like 5,000, then after 5,000 positive edges it will turn on, and then after 5,000 it will turn off, 5,000 turn on, off in a signal. So while that's running, I have essentially a non-stop like case system that will figure out what these buttons are interacting with stuff. So the default is always just, not default, that's the improper word because that's an actual thing, but it always starts by having a separate counter, and that is always going to be looping at a very small amount. Like for this is 10, and at every single time it's going to be reading in the switches, and you need to put a slight delay between the write and the read. And then from here on, I set that value to some variable, and then I have another loop going, and that's going to be checking once every 10 milliseconds, and it's going to take the value of the switches again. And if those match, that will send to that will pretty much decide, okay, there is definitely this signal here right now. And from that point, that is how you create a debouncing on the buttons, which essentially makes it so that, like, considering when you press the button down, it doesn't like just flat go from like on or off. It kind of bounces up and down a whole lot. And you don't want your signal to bounce whatsoever. So putting in this essentially 10 millisecond delay lets it be like, okay, this button has been held down for at least 10 milliseconds. This person is definitely holding this button down. What do you want to do? And so I have the counter again running, constantly checking for that. If it equals 0, then nothing happens. It goes back to the beginning and starts over. But if it equals if one of the button inputs is definitely not a 0 but a 1, it will then go to another case system to determine what is the new input or output for, not the input or output, the new marker for the frequency. And so the lowest button gets the like about 47,000, and that is the like marker point for a C5. And then I also set into that point for the LED bits, I set it to add 1. And then for the next button, I set it to the note above C5, which would be D5. And then I set that to add 2 to the, in binary, obviously, to the LEDs. And I go from there and I set the 8 buttons, essentially. And then after that, I repeat the debouncing process where I read in the inputs once every 10 milliseconds to see, oh, has this button been let go of yet? Because if the button value pressed down 10 milliseconds later is still down, then it needs to keep outputting this high or low frequency. But if it's let go, I need to set the frequency point to be 0, so that way nothing gets output ever. And then it will just start the case system over from there. That's essentially how the code is running at all times. And alrighty, that's pretty much this entire project. I really enjoyed this class a lot. This is one of the few subjects I've actually can say that I have fun working with in this class. I've learned quite a few things about the way FPGA works, and I can definitely see its application in many different, just general purposes in like everything. Like I can see why someone would need this to have things function. I'd hope to get a job working with something like this, just because again, this is one of the few things I have fun playing around with, and I understand it very well, and I feel like my skills could be useful to someone who would need someone good with FPGA. If you have any other questions, you can send me an email at tcco@uofh.edu. I cannot give you the code once again, so if you email me with that, I will ignore it. Thank you, Dr. Marpaung, for being a very knowledgeable teacher and professor. Those are essentially the same thing in this context, but you know what I mean. Thank you.